n boundary operation. N boundary. We define an n boundary. We define it as a set of all elements that can be written as the image of something or some element. Image of some element, we call it element. I think that's more formal, so let's stick to that. Some element in the n+1 chain group. That is some d where d belongs to Cn plus 1 of k. Then we call this C as the n boundary. Okay, and we denote the set of all n boundaries with Bn of k. B for boundary, n for n boundary, and we are working with a simplical complex, or in short complex k. And this name is natural because, you know, if you have a n+1 chain, a set of n+1 chain, or the n+1 chain group, and from there you take an element of that n+1 chain. Let's say you take an element that is a n+1 chain and you want to compute the boundary of it, right? And we said or defined the boundary operator in such a way that if you apply it on a simplical complex, it gives you the boundary of that simplical complex. So the boundary of this D will be given by this C. That's what it means. Now, while it is true that your n boundary is n cycle, the converse is not necessarily true. So this is an important remark. While it is true, always true, that an n boundary is an n cycle, the converse is not true. And you can easily see it, that if you have something as an n boundary, it will always be an n cycle, because if you recall that if you apply the boundary operator twice on something, that actually gives you a 0. Okay, we mentioned it a few minutes back. So how do you get an n boundary? From the definition we saw a few seconds earlier is that, let's say this is my n boundary, so this is the n boundary. It's coming from this operation, right? And now you want to see whether this n boundary is also an n cycle. So you just take del n Cn, just C. Then this is del n, and this is del n+1, and this is acting on D. So we are operating the boundary operator twice, and this is by definition 0. And you can even check it, like instead of D you can take let's say P0 P1 like this, and instead of n you would get 1 plus 1. So this del 2 del 1, and if you can apply that here and you can get 0. So in general notation, this is just this. Okay, so why are we doing all this? Because you might want to pause for a while and you want to think, okay, we are doing these chains, we are doing these boundaries, but why we are doing it? And recall that At the very beginning, when we started introducing these topics from algebraic topology, is that we said that we want to classify spaces as much as we can, and one of the way that we can do is to find a hole, whether our topological space has a hole inside it or not. So what we want to emphasize is that we are interested in things that do not have boundaries. I mean, we are interested in those things that do not form a boundary. Rather, from the first calculation they might look like boundaries, but what they actually do is that they induce a hole inside our topological spaces. So if I translate that sentence into mathematical language, what we are interested in is that we are interested in chains that are elements of the cycles, but they don't belong to the boundary. Okay, so if I write it down,